So, good afternoon, everyone, and welcome to this lecture. This is lecture number 12 in capacitance. Remember, we are doing capacitance and resistances together, and we will go ahead and see more stuff about capacitance, which is peculiar to capacitance. In the last lecture, we had seen the Nodal theorem for resistances, and we had seen the various cases in which you can apply the Nodal theorem and get the answer quite simply, especially for circuits where they have two nodes or two branches. We've seen how quickly the Nodal theorem can give us the value of current. We had also seen that if there is no resistance present between any two nodes, then the Nodal theorem becomes more easy because you know the potential difference between the 2 points, and then you can straight away get the values of current in each and every branch. Everyone remembers this, yes or no? Everyone remembers this. Okay, why there is a problem here? Okay. So now what we need to see, just for the purpose of understanding, we can also apply this Nodal theorem on to capacitors. And how will I apply this Nodal theorem for capacitors? Nodal theorem for capacitors. First, understand, and then I will give you time to note it down. Don't worry. How we can apply Nodal theorem for capacitors. So now let me make again the same circuit that we have used 2 or 3 times, and we have solved that circuit in different ways. So this is again the same circuit that I am going to draw, so that you understand that everything that we did in all the cases, we had solved this circuit using Kirchhoff's law, we have solved this circuit using Nodal theorem for resistance, capacitance, everywhere the same circuit, so that we understand that everything is similar. This is E1, this is C1, this is C2, this is E2, and this is C3. Everyone understands this? Yes or no? Everyone understands this? Remember this circuit, yes or no?
Yes.
Okay. Everyone is there in this universe only, right? Same universe, same dimensions, X, Y, Z
Yes,
axis.
sir.
Newton laws are valid. There, na? Okay.
Yes, sir.
Let's not jump onto some other universe. Just now I got WhatsApp message or on Twitter that some people in Wisconsin, USA, have seen some UFOs and some lights. Even I saw one light a few days back. It was just stationary in the sky, and I know that a UFO has come. But that UFO did not take me to another dimension. I'm still in the same dimension, and I hope you are also in the same dimension, in the same universe. Let's not worry about the UFOs anymore. This is point B, and this is point A. And again, I have grounded point B. So potential of point B becomes 0. And I can call the potential of point A as VA. I'll give you 2 minutes to think of how I'm going to apply the Nodal theorem. As you can see, it is exactly the same, same configuration, same everything that I have done for resistance. I'll give you a minute to think of how should I apply this, and if you can apply them on your own, that means you are good enough to do any question that comes. So I'll give you 1 minute to think about it and let me know if you can apply Nodal theorem on this one, and tell me what results you are going to get. So you have 1 minute. Okay, so you could not do it, that's not good, but still life has to move on. So I will assume that there is a charge Q1 which is moving like this. There is a charge Q2 which has moved like this, and there is a charge Q3 which goes in this branch. So this will get positive, this will get negative, this will get positive, this will get negative, this will get positive, this will get negative. Still the same concept comes. Q1 plus Q2 plus Q3 will be equal to 0. I'll just write it once so that Q1 plus Q2 plus Q3 is equal to 0. And then I will go in the different branches from A to B and find out the value of Q1. Can anyone tell me what will be the value of Q1? Looking at the diagram. Can anyone tell me the value of Q1 looking at the diagram? This branch. Looking at the diagram and this branch, can anyone tell me the value of Q1? It seems like no one can do that.
A minus C1 into C1.
Okay, that is correct. That is correct. VA minus E1 multiplied by C1. That is correct. See, it was so simple. You could have done it on your own. That would have given you a lot more confidence. Anyways, this path, green path, will give you the value of Q2. Can I hope that you can give me the value of Q2? Or I
A
am
minus E2 into C2.
VA minus E2 multiplied by C2. Can I hope the same thing in the third path?
VA C3.
VA multiplied by C3, that should be equal to 0. I did not have space, but if I understand this, I can straight away write the value of VA. Just looking at the configuration, I can just write the value of VA. And what is the value of VA going to come? E1 C1 plus E2 C2 divided by C1 plus C2 plus C3. That will be straight away the value of VA from all the diagrams that we got. Will be straight away the value of VA. Looking at the diagram, you can get the value of VA straight away. And it looks even less complicated. The original equation that I got from for the resistor. Can anyone recall what was the equation we got for resistors? It was E1 by R1 plus E2 by R2 divided by 1 by R1 plus 1 by R2 plus 1 by R3. As you can see, both the equations are exactly similar. The only difference is in place of 1 by R1, you have C1, and that will always come whenever you change over from a formula for resistor into the formula for capacitor. If capacitor is in the numerator, resistor will come in the denominator. I hope you have understood what I meant to say. Capacitor in the numerator and resistor will come in the denominator. In the denominator, we had C1 plus C2 plus C3. And in that case, it was 1 by R1 plus 1 by R2 plus 1 by R3. I'll give you 2 minutes. 2 minutes to understand this and note it down. And get it for you. So the question looks like this. Let us make it and get the answer. Question number 1. I have one battery like this. Let us say 2 volt. I have a battery, 2 volt. I have a capacitor here, 2 microfarad. Just try to make things symmetrical. 3 microfarad, 5 microfarad, 5 volt. And I now wish to find the charges appearing on all the 3 capacitors and the potential difference between the 2 points. Let me name these points for you also, between A and B, and I'll give you 2 minutes to solve this one. So how are we supposed to do this? Again, Q1 charge goes in this, Q2 charge goes here, Q2 and Q3 goes here. The first thing is the simplest thing. I can find out the value of VA. I have earthed this. So the value of VA will be 2 into 2 plus 5 into 5 divided by 2 plus 3 plus 5. So that straight away gives me the value of voltage as 29 by 10 volt. Now I can find the value of Q1. What is the value of Q1? Huh? Sir, I don't know. Jagdish has given me the answer. So it will be VA 29 by 10 minus 2
Q1 equal to 1.8.
multiplied by 2. Then I will try to find out the value of Q2. Q2 will be 29 by 10 minus 5. So you can see it will come negative. One of them has to come negative. Otherwise, the concept will be wrong. Then I will find the value of Q3, 29 by 10 multiplied by 3, and that will give me the required answers. Do we understand this, or this has gone above it saying bye bye?
Understood, sir.
Okay. Huh?
Yes, sir.
Thank God, sir. God is great, sir. That we have understood, sir. Now I'll take you back in the past. See, I have a time machine. And I don't have to go to different dimensions here. I'll take you go back. I'll take you in the past. Why you want to go in the past? Because in the past we had done a question like this. That was from your favorite book, SCV, page number whatever, question number 25, part D. And in this part D, you had to find out the value of VA minus VB. This part you have to find out the value of VA minus VB, and if I take you quickly, back. This was what we did on that day when we saw the UFO. This is what we did on that day. We also know the answer now. Today is the day. And we are back with the same question. Can we do anything better? This is the present, my dear friend, the same dimension that we are in. This is the present. And you have 2 minutes to show your talents, else I'll have to show mine. So, how do we do this? Again, the same concept. This is my point A and this is my point B, which is going to get Earth. But remember here, the battery are connected in the reverse order. So instead of E1 C1 plus E2 C2, it will be minus E1 C1 minus E2 C2 and minus E3 C3. Do we understand this, or above our heads going saying bye bye?
Understood, sir.
So VA, which is VA minus VB, will be minus 6 into 4 minus 12 into 2 minus 24 into 1 divided by, now you see, 4 plus 2 plus 1, and without much stuff, we end up with the answer very, very smartly and very, very quickly. How many of you got this? Please raise your hands. All girls and some boys. Boys are useless. Anyways, even useless stuff will is of useful is useful somewhere. Even a stop, a watch, a clock with a stop, it also gives you correct time twice in the day. So I hope the useless people will also get up. And in the next question will give me the answer. Everyone understand this? Once you get the value of VA, you can easily find out the charges. Instead of this VA minus E1 into C1, in this case it will be VA plus E1 into C1. Do we understand this? Huh?
Yes, sir.
Yes, sir. Yes, sir. No, sir. Then comes the next question, sir, to my favorite class. And I'm expecting an answer quickly. My favorite class consists of useless people, but I'm also useless. So two useless people make a good company. So can the useless people become useful? That is the question. And we are going to get the answer of this question in this question. Now, we have to find out VA minus VB in this question. This is the same question, part number 3. But the only good thing or the only bad thing or only the new thing is this beach wala resistor, beach wala capacitor, we don't know what is the capacitance of this capacitor. We don't know the capacitance of this capacitor. Even then, we have to find out VA minus VB. So the challenge has been thrown up. Let's see. My team of boys will do it, or the opponent girls will take it away. Stiff challenge. Let's see who gets this one. I am vouching for boys. How are we supposed to do this? I don't know the capacitance of this, but don't worry, if capacitance is not given, probably we will not need it. I will call it C. In any case, I will call this one as Q1, I will call this one as Q2, and I will call this one as Q3 just for the sake of doing it. And then I will try to find out the value of VA, and you'll see because of the particular arrangement what happens. So I go ahead and write the value of VA. VA will be equal to how much? Tell me. Look at the battery, look at the positive terminal, look at the negative terminal, and tell me what is the value of VA. How did I get to the value of VA? So if I go along the path of Q1, the negative terminal comes first. No, the negative terminal comes first. Yes or no? So this will be the negative part. So it will be equal to, oops, wrong color. That will be equal to minus 2 into 2. This comes from that blue part. Do we understand this? Huh? Or bye-bye? Bye-bye?
Understood, sir.
Then I go on this path, the green path. And the green path, positive terminal comes first.
Yes, sir.
So this becomes plus
Yes, sir.
2 into 2. This comes from the green path. Now, I don't have to divide it, but if you want to divide it, you can divide it. 2
2
plus
plus 2.
plus C. But whatever happens, the answer is going to turn out to be 0. The potential difference is 0. I don't need the value of C. I don't know the value of C. I don't need the value of C. You understand this or bye-bye?
Understood, sir.
So
Sir.
basically the potential difference across A and B is 0. So you can join it by a point. And now it becomes very simple to get the value of Q1 and Q2. Can anyone tell me the value of Q1 and Q2? Now there are 15,000 different ways of finding out Q1 and Q2. Out of those 15,000 ways, can you tell me what is the value of Q1? What is the value of Q1? Q1 will be minus 2 into 2 divided by 2. So it will be equal to -2 microfarad. Why it is coming -2? Because charge is not going in this way, charge is coming in this way. You understand this? Yes or no? Huh?
Yes, sir.
पक्का ना सर?
Pakka, sir.
कच्चा वाला पक्का और पक्का वाला पक्का और कच्चा वाला कच्चा और पक्का वाला पक्का. Okay.
Pakka wala pakka, sir.
Q2. 2 into 2 divided by 2. So it is +2. So basically what is happening, bacha, here is this charge, the green charge is going like this. Ding, 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 ding. So this is how charge is flowing. And there is no charge going in this pudding branch. Do we understand this? The circuit just flows like this. Do we understand this?
Yes, sir.
Pakka now, sir?
Yes, sir.
Okay. Shall we move ahead in life?
Yes, sir.
Okay, so this was what we had to understand. Yes, beta.
Sir, why are you dividing it with 2, sir? Charges.
Oh. Sorry. I made the mistake. So why did I divide it by 2? Yes, even I don't understand why I divided by 2. I must be in some other universe, parallel universe where it has.
Sir, we said 4.
Yes, it is 4 and 4. Sorry. I must have been in a parallel universe where, sometime since I am very excited about time travel and UFO, sometime I get into some other dimension where, all these funny things happen. Right now I'm back in the dimension, and this dimension is -2 into 2 and +2 into 2. Okay. We got this?
Yes, sir.
So back in the dimension, and let us now move ahead and venture into the next topic. Again, this is a topic which is peculiar to your capacitance only, and therefore we now come back to capacitance in the same universe. The next heading that we are going to write is known as dielectric. The next heading that we are going to write is dielectric. Now, what do you mean by dielectric? What do you mean by dielectric? Yes. What do you mean by dielectrics? Anyone? Huh? Sir, this is the first time we are hearing the word dielectric. We don't know, sir. Huh? What do you mean by a dielectric? Hmm? No one knows it? So basically, yes. What? Dielectric, yes. When I say, then only you say. Yes, say.
Which does not allow current and allows electric field.
It does not allow current, but it allows electric field. Okay, so dielectrics are insulators. Are basically insulating bodies, insulating materials. Insulators. Basically, they are insulator or insulating mediums. They do not have free electrons that can move around here and there. The dielectrics are basically insulators. Now, but we must understand that nothing is perfect. Even conductors are not perfect. They also have resistance. So dielectrics are also not perfect. They are insulators. They don't have free number of electrons, but when you place them in an electric field, they don't have free electron, but they have positive and negative charges because everything is made up of atoms and nucleus. Yes or no? So they have charges, they have electrons, and when you put this dielectrics in the presence of an electric field, what happens is there is a small local displacement or distribution of charges. You may not understand it in so deep. Basically, dielectrics are insulators. Basically, dielectrics are insulators, and when you place dielectric in an electric field, something happens. And what is that something that is going to happen? We are going to see that. So don't worry about this. But these dielectrics, remember, these dielectrics also have atoms and nucleus, atom, nucleus, and they also have electrons. They are not free. But if you put this dielectric in a field, and if this field is very high, now what is this field going to do? Whenever there is an electric field, this electric field will cause your electrons to move, your positive charges to move in the same direction, and your electrons will be accelerated in the opposite direction. Do we remember this? Yes or no? So this electric field basically gives these electrons energy, and if you apply a sufficiently high electric field, the electrons which were bound previously now can become free, and this insulator, which was an insulator, now becomes a conductor. That maximum field is known as the dielectric strength of a dielectric. They lose their insulating properties, and now they become the good guys and they become conductors. Do we understand this?
Yes, sir.
So basically dielectric strength, and you might hear this term. Dielectric strength is nothing but the maximum value of electric field that a dielectric can tolerate without breaking down. Breaking down is okay, I've lived my entire life as insulator. Now let me live the life as a conductor. So it will not break down and it will continue on its journey as an insulator. The maximum electric field that it can tolerate is known as the dielectric strength, and the unit is volt per meter. So whenever you hear the term dielectric strength, dielectric strength of a dielectric, only think about it is the maximum electric field that it can tolerate. Everyone understand this, or is it gone above or saying bye bye? Huh?
Understood, sir.
Now these dielectrics are insulators. Now these insulators are made up of atoms, nucleus, and all those things that we study in chemistry. Now there are two types of molecules. And again, I go to chemistry and I hate chemistry, but I'll have to go a bit into chemistry here, which I don't know and which I don't like. There are two types of molecules that you might come across. One are known as polar molecules and the other one are known as non-polar molecules. Any idea about this polar and non-polar molecules? Yes or no? Huh?
Yes, sir.
So everything is made up of atoms and molecules. So there will be two types of dielectrics, polar and non-polar. Understand this? It is going above or saying bye bye. The first one is a polar dielectric. Now, my chemistry is very weak, but I see that you get almost 100 in chemistry. So now I would shift the focus back and ask you, what do you mean by a polar dielectric? You will tell me because you are getting a lot of marks in physics, in chemistry, and I never got so many. Yes. What are polar dielectrics? Huh? So we don't know. We get marks, but it's because of blessings of God and the chemistry teachers. We don't know nothing. Huh? No idea? We don't know anything, sir.
Charges are included in dielectric.
What?
Charges are included in dielectric.
Charges are included in the dielectric. Oh God. No, that is definitely. Can you give me an example of a polar molecule? Chalo.
Water, sir.
Water. Water. Water is the essence of life. Without water, nothing happens. Civilizations have flourished only near oceans and seas, bodies of water, because of water, nothing happens. A polar molecule is water. Now, what do you mean by polar? Water consists, if I remember from my 11th standard chemistry, it consists of hydrogen and oxygen. And hydrogen is positively charged and oxygen is probably negatively charged. The centers of the positive and negative charge does not coincide due to the asymmetric shape of molecules. Molecules are not symmetric, and therefore the center of the positive and the center of the negative charge do not coincide. Do we understand this? Yes or no?
Sir.
Now, whenever we talk about polar molecules, each molecule has something known as a dipole moment of its own. Have you heard about this term in chemistry? My chemistry is very bad. Don't expect
Yes,
me.
sir.
Sometimes chemistry also works nicely. Each molecule has a permanent dipole moment, but you can see there are infinite number of molecules even in one drop of water or any polar thing. There will be infinite number of molecules and infinite number of dipole moments, but these dipole moments are randomly oriented. If one dipole moment is like this, another would be like this, one 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 would be like this. So basically their average dipole moment is almost zero. The average dipole moment of this material per unit volume in the absence of an electric field is nearly zero, because randomly they will just cancel each other out, because remember dipole moment is a vector quantity. So one dipole moment is like this, one is like this, they will cancel each other out. Do we understand this, or bye?
Understood, sir.
Now, in the absence of dielectric field, the dipole moment is definitely almost zero. But in the presence of a dielectric, in presence of an electric field, and now go to that part of electric dipoles which you told me that you have done, and that's why I skipped it. Now, whenever you place this dipole in an electric field, then what will happen? What happens? What happens? I skipped that part because you told me that you understand dipole moment. Yes, I skipped that part. What happens when you put this dipole in an electric field? They will align itself in the direction of electric field. Yes or no? Stable equilibrium, we call it. If the electric field is in this direction, the dipole moment will be in this direction. They will align itself in such a way. Do we understand this?
Yes, sir.
Even if you don't understand it, you have to say yes, sir, because you said that you know it. So whenever you put this dipole in an electric field, this polar molecule in an electric field, it will align itself and you will have a net dipole moment induced in this polar molecules or polar dielectric. The example of polar molecule, I had no idea. Water, something to drink. Alcohol, definitely something to drink. CO2, not drinkable. HCl, definitely not drinkable. Ammonia, medical uses, drinkable probably. Do you understand this polar dielectrics? Yes or no?
Yes, sir.
Everyone has noted this down? Huh? Noting down, sir? Shall I give you time or shall I move ahead in with life? Life has to move on. Okay, I'll give you 2 minutes. Note it down. So these were polar dielectrics. But then again, chemistry tells us there are the other types of molecules as well, which are known as what? My chemistry
Non-polar dielectric.
non-polar molecules, and therefore non-polar dielectrics. Now, since we understand polar very nicely, now you are going to tell me what are non-polar dielectrics. Why I'm writing electrics? Non-polar dielectrics. These non-polar dielectrics come from your non-polar molecules. So, fatapat, tell me what is the first thing? No one knows this. It's exactly opposite of the polar one, bhai. Can you name a non-polar molecule? Yes or no? No, yes. Sun. So the first thing is, in the absence of electric field, the center of positive and center of negative charges coincide. Symmetric molecule, N2, O2, F2, symmetric molecule. The center of the positive and negative charge are same. So the net dipole moment is 0 in the normal state. There is no dipole moment at all. Polar molecule have a very small dipole moment, but non-polar molecule are absolutely 0. But what happens is, when we have an electric field, when we have this dielectric put in an electric field, again there will be some induced dipole moment, and this is a very important term. They will get an induced dipole moment. So no matter whether it's a polar molecule or it's a non-polar dielectric, when you put them in an electric field, if they are not in the electric field, almost their dipole moment is 0. But as soon as you put them in the electric field, they will have some net dipole moment. Have we understood the concept behind this? Yes or no? Have we understood this?
Sir,
Have we noted this down?
noting, sir.
Okay. Note it down, and then I'll give you a snapshot. Probably make you understand. Have you noted it down, everyone?
Sir.
Shall I move ahead?
1 minute, sir. Completed, sir.
Okay, that means we can move ahead. Now, you can see this. This is again, I'm putting everything in the tabular form. First, listen to me, and then I will give you time to write. Don't worry. Everyone can see this. Polar dielectrics are molecules like water and alcohol. You don't have to write anything, just understand the concept. You can see that the center of positive charge and the center of negative charge are not coinciding. Do we see this? Pink one are the positive charges, green one are the negative charges, center is not coinciding. But if you look on the right hand side, the center of positive charge and the center of negative charge in this case is coinciding. Do we see this? Yes or no? So these type of dielectrics are known as non-polar dielectrics. Now, first listen to me, then I'll give you time to write. Then you can see in the absence of a dielectric field, they are oriented randomly, and therefore the net dipole moment is 0. Do we understand this? Net dipole
sir.
moment is 0. But what happens is when you put them in an electric field, and if the electric field is going in this direction, if you put them in an electric field which is going in this direction, what happens is they will acquire, all the dipoles will get aligned and they will acquire a dipole moment. Same is the case here. When you apply an electric field, the center of positive and negative charges, they shift. Do we understand this? Have you understood, everyone? Yes or no?
Yes, sir.
I'll give you 2 minutes to just draw the diagrams and understand what I have said. Everyone understood? Everyone got this?
Yes, sir.
I'll give you 2 minutes to go through this diagram and draw it, polar, non-polar. Let me know once you're done. Okay. So what do we see in this initial discussion of dielectric is, whenever you put a dielectric inside an electric field, whether there is the polar dielectric or a non-polar dielectric, a dipole moment is induced in the dielectric. A dipole moment is induced in the dielectric. Do we understand this? This phenomena is known as polarization. This phenomena is known as polarization, and that is going to be our next heading, polarization. It has been polarized. Polarization. Polarization. What is this phenomena of polarization? First, listen to me. I'll give you time, then you write. Whenever a dielectric, you can write this part. Whenever dielectric is placed inside an electric field, a dipole moment, and I will call dipole moment as, well, let me call this dipole moment as M. A dipole moment is induced in the dielectric. This phenomena is known as polarization of the dielectric. This phenomena is known as the polarization of dielectric. Now listen to me very carefully. Listen to me very carefully, and then I will give you time to write. Where do I find a suitable diagram? Where do I find a suitable diagram? I will draw it. If I can't find it, I will draw it. So, see, let us assume that first you listen to me, then you can write. This is a dielectric. This is a dielectric, and I've placed this dielectric inside an electric field, and this is my electric field. An electric field goes like this in this direction. The value of this electric field, let us say, the value of electric field is, let us say, E vector. Now, because of this dielectric field, what happens is all the dipoles get aligned in the same direction. Because of all these dipoles getting aligned in the same direction, just give me a minute. I would better show you one more diagram that might help you in understanding this. Give me a couple of seconds. Better to show you that diagram that might help you. If I remember correctly, this diagram should have been here. Else I will have to make it. Well done. Let me take a snapshot here. And that snapshot should do my job. So, just trying to make you understand this. See, I hope you can see this, right? You see this? We have applied an electric field on a dielectric. I hope you can see this now. We have applied an electric field on the dielectric, and all these dipoles, they get aligned. Do you see their alignment? Do you see their alignment, everyone? Now, what happens because of this alignment is inside the dielectric, if I call this space as the blue space, inside the dielectric, all the charges will cancel each other out. But on the edges, if you look at this right edge and you look at the left edge, on the left edge, you will have negative charge, which will not be getting cancelled. And on the right edge, you will have some positive charges left. Because of this positive and negative charge, which is getting induced in this dielectric gets a dipole moment, and the dipole moment of this dielectric is always from the negative charge to the positive charge, and let me call this dipole moment as m vector. This phenomena is known as polarization. So how do I show it? On my diagram here, I will show negative charge on this side, and I will show positive charge on this side. This is what happens an electric field. It will get a dipole moment induced, and the direction of that dipole moment will be same as the direction of electric field. Do we understand how this is done? Anyone understands this?
Yes, sir.
Can I have a raise hand? Now I'll give you 2 minutes. Draw the diagram. This is just for your understanding and nothing else. I'll give you 2 minutes. So what do we see here? This phenomena is known as polarization. Because of this polarization, bacha, what happens? Now, remember, simple things. If you can remember them, you can get a question. If you get a question on polarization, that will only be in JEE Advanced. Okay. So whatever we are doing is only for JEE Advanced. For JEE Mains, the concept is very simple. So please pay attention, because we are not going to get any chance to revise this. So if you want to understand polarization, you can also write this polarization in this form, and I will just give you I'll give you the other way of understanding this polarization. This is nothing but the alignment of the dipole moment This is nothing but the alignment of the dipole moment in the direction of electric field when when a dielectric is placed inside the electric field. Everyone understands this? Polarization is nothing but alignment of dipole moment in the direction of electric field. It is as simple as that. Everyone understands this? Yes or no?
Sir.
Now, this polarization, whenever we talk about this polarization, this is understood by a vector quantity, and that vector is known as polarization vector. Remember, what we are doing is only for JEE Advanced. It has got nothing to do with JEE Main. Polarization P vector. Now, what is this polarization vector? This is a vector that tells us to what extent or to what degree the dielectric has been polarized. How much the dielectric has been polarized, it is given by this quantity, which is known as the polarization vector. Do we understand this? So it is a vector quantity. It is a vector quantity that gives us, that tells us up till what extent, up till what degree has your dielectric getting polarized. Now, again, how do I find this vector? This dipole moment vector is, this polarization vector is the net dipole moment induced, net dipole moment which is induced per unit volume. Per unit volume. What is the net dipole moment which is induced per unit volume? And if I say that the net dipole moment is m, so this will be m vector divided by v, where v is the total volume of the dielectric. Do we understand this? Do we understand this? Yes or no?
Yes, sir.
Pakka, everyone understands this? Okay, and what is the direction of this dipole moment? The direction of this dipole moment will be same as the direction of your induced dipole moment, and the direction of induced dipole moment is same as the direction of the applied electric field E. So all are in the same direction. Do we understand this?
Yes, sir.
Now there is one more way in which you can understand this polarization vector. Now listen to what I am going to say very carefully. Once you understand this, then you will write it. I will give you time to write, don't worry. Again, remember, I'm repeating it for the nth time. This is only for JEE Advanced that we are doing all this. Now, whenever a dielectric is placed in a field, electric field, you will see that negative charge will appear on one side and positive charge will appear on the other side. The charge which is appearing on the dielectric is known as the induced charge. The charge which appears, if I say that the charge which is appeared is minus q here, the charge which has appeared is plus q here, I will write I. What does this I mean? This I means this charge is induced. So the charges which appear on the outer surface of the dielectric is known as the induced charge. That is the next thing that we are going to write. That is the next thing that we are going to write is the charge which appears, on the outer surface, charge appearing on outer surface is known as induced charge. and you can write it as Qi. So far, so good. So far, so good. Do we understand this, or just has gone above our head, saying bye-bye?
Understood, sir.
Now, then we have one term which is known as sigma I, and I will not tell you what is this sigma I because you are going to tell me what is this sigma I. What is this sigma I? What is this sigma I?
First chance. Second chance.
What? Induced
Use charge on surface.
density. Charge which is induced per unit area. Charge which is induced per unit area is known as the induced charge density, and that is sigma I. And what is the most important aspect that you must remember? The most important aspect that you must remember here is the magnitude of P, not the direction, because P is a vector and surface charge density is a scalar. The magnitude of P is same as the surface, the induced surface charge density. The direction is same as the direction of electric field. The magnitude is same as surface charge density, and therefore you can understand the SI unit of this polarization vector, a very important term. The SI unit of this polarization vector will be coulomb per meter square. Do we understand this? Everyone has understood this so far, so good, or it has gone
Yes,
above
sir.
that thing? Okay, sir.
Understood, sir.
Bye bye, sir. Forgive us, sir. We can't do anything anything else, sir. Okay, now I'll give you 2 minutes. Understand it and note it down. 2 minutes. Now let me again go back to the same diagram. Now, this is the original diagram which we understood. Now, just for the sake of some similar thing, I will call this outside field as E naught. You can just change the field from E to E naught. Outside field is called E naught. E naught is the applied field. Do we understand this? This E naught is the field in which this dipole, this dielectric is placed. Now, because of this applied field, which is given in blue, which is given in pink, charges come on the opposite faces. This face gets negative charge, this face gets positive charge. Yes or no? Now, because of this positive and negative charge, this positive and negative charge will induce a field, will cause a field because of this positive and negative charge. Yes or no? Yes or no?
Yes, sir.
In what direction that field would be? The dipole moment P, the dipole moment P vector is in this direction. Okay. In what direction will that field be, which is created inside this dielectric because of positive and negative charges appearing? Yes, it's a very simple question. Yes. What would be the direction of the electric field? No one knows it. No one knows what will be the direction of electric field, which is caused by a positive and a negative charge. No one knows it. Okay, no one knows it. So it always goes from positive charge to negative charge. So the field which is being induced inside this dielectric, and I will call it as EI vectorly. EI, this induced electric field inside this dielectric will be going from the positive charges to the negative charges. Do we understand this, or this was too much for you to understand?
Yes, sir.
Chalo. Now, if I have to find out the net electric field inside the dielectric, now I am just continuing from where I left. If I have to find out, very important point, if I have to find out the net electric field inside the dielectric, now this dielectric is actually subjected to two fields. This dielectric is subjected to two fields. One is the outside field, the external field, and one is the internal field. Yes or no?
Yes, sir.
The net field will be the vector sum of this. Yes or no? So when I write
Yes,
vector,
sir.
write it vectorly like this. Yes or no? I must write it vectorly like this. If I just want to write out the magnitude here, the magnitude of this will be E naught minus EI. Yes or no? This is magnitude wise I've written. The same thing. We understand this? Yes or no? Now we have found out that this net electric field inside this dielectric is equal to the external field E naught divided by a constant K. Please listen to me very carefully. We found out that this electric field, this net electric field inside this dielectric can be written as E naught divided by K. This K came to be known as what?
Electric constant.
This K came to be known as your dielectric constant. You can call it dielectric constant, or we can also call it relative permittivity. Do we understand this? So this is gone above or saying bye bye sir, हो गया sir, माफ कर दो.
Yes, sir.
छोड़ दो हमको. I'll give you 2 minutes to write down. I will ask you to draw a fresh diagram. Draw a fresh diagram on your own. Mark the original field. Mark the induced charges. Write sigma minus sigma plus. Write E. Then write E naught. Then write EI. Then write the net electric field so that everything is clear in your head with your own hands. Because you might make a mistake here. It looks very confusing because we are still not done. We have to still understand 2 or more things here. Everyone understands this? I'll give you 2 minutes to do it on your own. Again, for the NET time, this is not for JEE Main. What is the last point? This net electric field inside the dielectric is always equal to E naught by K. You just have to remember it. There's nothing to understand there. We have to remember this. So the net electric field inside the dielectric is E naught by K. That is the last point that you wanted to understand. That was the point you were talking about.
Why did we get E naught minus E electric field induced?
Ask your question again.
Why did we get E naught minus, sir?
Why did we get E naught minus, sir? Have you drawn the diagram of that I asked you to draw? Have you drawn the diagram, beta?
Yes, sir.
Can you show me the diagram on the camera? Can you show the diagram? Come first. Show the diagram on the camera. Jaldi, jaldi, we don't have time. Come fast. Come fast, come fast. I can't see it. Anyways, what I wanted to see whether you have drawn the direction correctly or not. Have you drawn the direction of these two fields like this?
Yes, sir.
Yes, sir. So what will be the net electric field? One field is going in the right, one field is going towards left. What will be the net field? If I talk about in scalar terms, vectorly, they are the vector addition. One is going in this direction, the other one is going in this direction. What will be the net field? Yes. What would be the net field? What would be the net field? This field is going in this direction. This field is going in this direction. What would be the net field? Tell me. Still don't understand? One field is going like this. This is E naught. One field is coming like this. this is EI. What will be the net field?
Minus EI, sir.
Yes, beta?
Minus EI.
E naught minus EI. What do you did? What do you not understand here? That means you have not drawn the diagram. Is that so? That is why I said to do it on your own. Have you
sir.
understood it now?
Yes, sir.
That is the faida of doing things with your own hands, that you understand what you are not going to understand. Otherwise, you will not understand what you not understand. One is in this direction. So if you call this as positive, this becomes negative. No matter how you take it, that is there. Okay. Now, let us now move ahead. Let us now move ahead. And let me now use this same concept in a capacitor, because we are going to put this dielectric inside the capacitor. So let me now put a capacitor here, and let me put this as the positive plate of the capacitor, and let me put this as the negative plate of the capacitor. So this is the positive plate of the capacitor. First, you listen to what I'm saying, then I will give you enough time to draw and write. Now, because of this positive and negative plate of the capacitor, there will be an electric field inside the capacitor, yes or no?
Yes, sir.
That electric field will be going like this, yes or no?
Sir.
Let me call that as E naught. This is the original field. Okay. Now what I'm going to do here, bacha, please listen to me very carefully. Do not be in a haste of writing. You can write it. You are good at xeroxing things, I know. This is, let us say, a dielectric I have put. Now, because of this dielectric that I have put, something will happen. Who will tell me what will happen? This is a dielectric. What will happen?
Realization.
What will happen? On this side, on the left hand side, what charge I will get?
Negative.
On the left hand side, I will get negative charge, and on the right hand side, I will get
Still.
positive charge. Okay, good. Now let me write the negative charge. Let me write the negative charge as minus Qi, and let me write the positive charge as plus Qi. We understand this up till now. So far so
Yes,
good.
sir. Yes, sir.
Because of this, what will happen? You will have an electric field which will be coming like this. Yes or no?
Sir.
And who will tell me what will? Okay, EI. Now there will be an induced electric field. Now because of this induced electric field, the net electric field. Now remember, this green that I'm drawing is the net electric field. And I hope that you understand. This green thing that I'm drawing is the net electric field. Do we understand, everyone? This green electric field is the net electric field. This green electric field is the net electric field inside the dielectric. Let me write it as E net. What will be that value of E net? Can anyone tell me?
Minus EI.
E naught minus EI. Yes or no?
Yes, sir.
Everyone understands what is happening? Now this E naught minus EI will be equal to E naught by K. This is what we have understood. That is the dielectric constant. Yes or no?
Yes, sir.
Okay. And from here, I can write E naught into 1 minus 1 by K. First, listen to me. I will give you time to write. That will be equal to EI. We understand this? So far, so good? I'm taking a lot of time to write this just because I want you to understand this once and for all. So far, so good? Now, this E naught, if you remember from the capacitor, can be written as sigma naught by epsilon naught. Electric field inside the capacitor, sigma by epsilon naught. Yes or no?
Yes, sir.
into 1 minus 1 by K. Now I can write this one as sigma induced divided by epsilon naught. So this epsilon naught will get cancelled and I will get a very beautiful formula for the surface charge density which is induced, and the formula is right now before your eyes. This is the charge induced on the surface of the dielectric. Do we understand this? This much charge will come on the surface of the dielectric. This is the surface charge density. From here, bacha, I can find out the value of Qi, which is the charge induced. That will be equal to Q naught, your original charge. This is your Q naught. This is your Q naught. We understand this? Yes or no? And this is your Qi. This is your Qi. Do we understand this? Or this is going above our head saying bye bye, sir, bye bye, sir. We are going, sir. Please don't stop.
Yes, sir.
Into 1 minus 1 by K. Some very, 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 very important result for JEE. And when I say JEE, I mean JEE Advanced. This is where we finish everything that we need to do about dielectrics theory wise. Again, we'll give you 2 minutes. Starting from the first point, when I told you what is polarization, to this point, I'm telling you what is this sigma and what is this Qi, I'll ask you humbly to please go through this and once and for all understand this and lock it forever. I'll give you 2 minutes, 3 minutes. So up till now, we have seen what happens if we insert a dielectric. If we put a dielectric in an electric field, it gets polarized. Now, when you have a capacitor which is charged and you put the dielectric inside the capacitor, same thing happens. The dielectric gets polarized. Now, we will write the next heading. And what is the next heading? The next heading is known as effect of dielectric on capacitance. Effect of dielectric on capacitance. Now we venture into the JEE main territory as well as JEE advanced territory. The effect of dielectric on capacitance. What happens if a dielectric is inserted inside a capacitor? Now, what we always desire, we may not get it, but what we always desire, now what is the use of a conductor? The use of a conductor or a capacitor is that it can store charge. No, not charge, I should say. What do you mean by capacity of a capacitor or capacitance of a capacitor? This ability to store what? Do we remember what was the capacitance of a capacitor?
Charge or energy, sir.
Energy. We want more and more energy, not charge. Let us take the charge out. We want more and more energy to be stored in the capacitor. And capacitance is that ability. So we are trying to increase the capacitance of a capacitor by different means. Now, what are the means by which you can change the capacitance of a capacitor? Remember, the original formula for capacitance of a parallel plate capacitor was like this. See, the capacitance of this capacitor is epsilon naught A by D. Now, if you want to increase the capacitance of a capacitor because you want more and more energy in less and less space, you know, when computers began, only 1 MB of data was stored in a huge hall with I don't know how many square feet allocated just to store 1 MB of data. And now in this small phone, you will have 1 TB of data, and this in this small chip. So basically what we are trying to do is to put more and more energy inside the capacitor. Now one way of doing it is increasing the area, but you can see even if we have a sphere of the size of Earth, this capacitor is only 700 something millifarad. So increasing the area is not the desired thing, because it will make the capacitor bigger. We cannot use Earth as a capacitor. The next thing is you can decrease the distance. Now if you bring it very close, and we will see that this plate is positively charged and this plate is negative charged, they will try to come close to each other. So it becomes very difficult to keep on decreasing the distance, because after a time you will not be able to keep them apart. What is the third way of changing the capacitance? What is the third way of changing the capacitance?
Permittivity, sir.
Yes.
Increasing the relative permittivity.
Yes. We cannot change the absolute permittivity of air, but what we can do is we can change the medium which is there inside the capacitor. Now, what do you mean by changing medium? We can put this capacitor in air. Air is one medium. We can put this capacitor in oil. We can put this capacitor in alcohol. We can change different medium, because these different mediums are nothing but they are dielectrics. Yes or no?
Yes, sir.
So the same thing is achieved when you insert a dielectric slab inside a capacitor, or you dip this capacitor in a container of oil or alcohol. You change the medium between the capacitor plates. Since you change the medium between the capacitor plates, you change the capacitance of a capacitor. Do we understand this? Yes or no?
Yes, sir.
Now, remember we talked about this dielectric constant K. Now remember this dielectric constant K for insulators. I must add it here. For insulators, what is the value of this dielectric constant from where to where it lies? Let me first clear that point. What is the value of this dielectric constant K for an insulator? Dielectric. From where to where it varies? Any idea? It varies from 1 to infinity. It varies from 1 to infinity. It varies from where to where?
Unto infinity.
It cannot lie between 0 and 1. Now, if you know that for insulators, it varies from 1 to infinity, applying some common sense, can you tell me what will be the value of K if I have to write the value of K for conductors?
Infinity, sir.
Yes?
Infinity.
Yes, the value of K for conductors is infinite. Everyone understand this, or this is going above it saying bye-bye? I've tried to take this topic as slow as possible, because this is what I think confusing. This is my point of view. I don't know your point of view, but no one understands dielectric and no one understands polarization. No one understands what is happening. That's why I'm going to go slow. Do we understand that the dielectric constant K for a conductor would be infinite? Do you understand this?
Yes, sir.
Now that brings to a very important result. Now, if I put the value of K as infinity for a conductor, if I put the value of K as infinity for conductor, if I put the value of K as infinity for conductor, so if I put, instead of a dielectric slab, if I put a conductor in between, then what will happen?
Charge used is 0, sir. QI becomes 0.
For conductors, oops, why I'm writing O? For conductors, For conductors, the induced charge Qi becomes same as Q naught. Yes or no?
Yes, sir.
Yes, sir.
So whatever charge is there on the original capacitor plate, same charge comes but negative on the samne wala plate. Do you remember? One plate. If this plate has positive, this will become negative. Remember that? Huh? See, same thing coming now. And your E net becomes E naught by infinity, so it becomes 0. So again, we come back to the same principle. Electric field inside a conductor is 0. Can you relate this dielectric with conductor? Are you able to relate it and understand what is happening? Or it is going above or it's saying, sir, ho gaya sir, maaf kar do, aage बढ़ो."
Understood, sir.
Okay. So this is what that happens for a conductor, but we are not talking about conductors. We are talking about what happens when you insert a dielectric inside a capacitor, and my thing is stop responding. Arey, do something, bhai. Sometimes now it has worked. Sometimes your this thing also becomes tight. Okay. Now we are going to see what happens inside a conductor, but again there are different cases that we have to understand. The first case is completely filling. Completely filling. What do you mean by completely filling? I will put the dielectric in such a way that it fills the space completely. Nothing is left. Literally nothing is left. Do we understand this? Completely filling. You understand this? And again, this one, I completely filling. Let me not make too many sub cases. Otherwise, it just becomes impossible for you to understand. Completely filling. So how does this case come? So I have here, let us call this as case number A here. I have this capacitor plate and I fill a dielectric completely filling up the space. Okay. I'll have to do it again. So this is the dielectric. This is the capacitor. And this is the dielectric. And I cannot make it completely filling. So I'm just trying to make it almost filled. So this is the dielectric and I've completely filled up the space. Let me call the area of the plates as A and the distance between the plates as D. And let me call the dielectric constant of this this dielectric as K. So what I see here is I am completely filling it up. I'm completely filling it up with a dielectric of dielectric constant K. What is going to happen now? What will happen to the capacitance of the capacitor? Because remember, the only thing that we are concerned about is changing the capacitance of this capacitor. If I call the original capacitance, the black one, as A epsilon naught by D, that is the original capacitance of this capacitor without the dielectric. Now I've pushed the dielectric inside this capacitance. The new capacitance C dash becomes K times A epsilon naught by D. The capacitance becomes K times, and that is why this dielectric becomes such an important tool. If I can find a dielectric whose dielectric constant is very high, So, because their dielectric value, the dielectric constant varies from 1 to infinity. So if I can get a capacitance with a dielectric whose in value is very high, 1000, dielectric constant 1000, I will increase the capacitance 1000 times. Do we understand this? And that is why this becomes a very important aspect of capacitor, to increase its capacitance. Do we understand this? So you can just write it here. C dash by C in this case becomes equal to K. Your capacitance is going to become K times the original capacitance. Now, whenever this question comes, when this dielectric is filled, there will be two types of conditions under which this dielectric will be filled, and you will understand those conditions when question comes. So first, listen to me very carefully, and then I'll give you time to write. Now, whenever this question comes, now this dielectric can be inserted under two conditions. The first condition is you charge the capacitor first. You first charge the capacitor by connecting it to a battery, and then you remove the battery. And now you insert the dielectric. So this is known as battery removed case. The second is you keep the capacitor connected to the battery, and then you insert the dielectric. Is the two cases clear to everyone? Are the two cases clear to everyone?
Once repeats.
The first case is you have a capacitor, you connect to a battery, you charge it. Once it is charged, you just remove the battery and put it one side, and then you insert the dielectric. The second case is you have a capacitor which is connected to a battery, and then you are inserting the dielectric. Do we understand this?
Yes, sir.
In both the cases, case number pink is battery removed, there is no battery. Case number green is battery is connected. In both the cases, what you see is the dielectric is completely filling up the space. The capacitance becomes K times. But the other things you have to understand. When the battery is removed, capacitor is isolated. And if something is isolated, if a conductor is isolated, its charge will remain same. So if Q dash is the final charge, that charge will be same as Q, the initial charge. Do we understand this? First, understand, then write. Do we understand this? But in the second case where the battery is connected, the charge on the capacitor plate becomes K times. So that is the difference between the two cases. In case number one, the potential. In case number one, the potential across the capacitor plate, changes. Charge remains same, but potential becomes 1 by K. But here, since the battery is connected, the potential difference remains same. In the first case, since the potential difference becomes 1 by K times, electric field becomes 1 by K times. But in the green case, since the potential is same, electric field remains same. And then you have the effect on the energy. In this case, Q square by 2C is the formula we will use. Q remains same, C becomes K times, therefore the energy becomes 1 by K times. Here, since the voltage is same, I can use the formula half CV square. Since the voltage remains same and C becomes K times, the energy, the formula is written wrongly, the energy becomes K times. Do we understand this? Everyone has understood the two processes?
Yes, sir.
Now I will give you 2 minutes to note them down. you don't understand anything, please ask. Here also, remember that sometimes you might get a question where they will not tell you whether the battery is connected or battery is disconnected. Remember, if they don't tell you whether the battery is connected or whether the battery is disconnected, you always assume by default that the battery is disconnected. If ever you encounter a question where they do not tell you whether the battery is connected or whether the battery is disconnected, you assume that the battery is disconnected. Do we understand this?
Yes, sir.
Okay. Have you noted this down, everyone?
Yes, sir.
Can I give you a question now? Can I give you a question now?
Yes, sir.
Anyone has noted this down?
No, sir.
This is the question that we are going to encounter. Okay, you can't do this because we have not done these cases. Sorry, I'll give you this question. That was partial filling. We can't do it now. So we'll just do this one first. There's an air-filled capacitor, 1 picofarad parallel plate capacitor. When the plate separation is doubled and the space is filled with wax, the capacitance increases to 2 picofarad. What is the dielectric constant of wax? It is completely filled up with wax. What is the dielectric constant of wax? Can I have an answer?
Yes, sir.
Yes, beta.
Option
Option
A.
Option A. Take a deep breath. Deep breath. Open your eyes and see. Only the 4%, not the 96%, which we can't see. Only see the 4%. And then give the answer again. Anyone there with an answer? No one knows, so I'll have to do this. How are we supposed to do this? Capacitance is epsilon naught A by D. Now, the new capacitance. This is the original capacitance. And this is given as 1 picofarad. What is the new capacitance? C dash. Can anyone tell me what is the new capacitance?
Input to epsilon by 2D.
K times
A epsilon by 2D.
2D. That is 2. So from here, you should get the value of K beta. What is the value of K? It has to come 4. I hope you understand this. Yes or no?
Yes, sir. Yes.
Please be careful, beta. Simple mistake and it is -5. And whatever hard work we are doing goes down the drain. Please be careful. I'll give you one more question before we end this class. Anyone understand this question? How it is done?
Yes, sir.
Pakka?
Pakka, sir.
Well, I'm not able to get it. This is hanging, so I will give you that question in the next class, and I will continue with this dielectrics in the next class, because we'll have to do a lot many questions on this. So I'll continue with this class in the next class. In the next class, we'll try to do more questions on dielectric. What we have understood today in this class on dielectrics is, whenever a dielectric is placed inside an electric field, it gets polarized and the charges are induced. The polarization is given by polarization vector, which in magnitude is equal to the surface charge density, induced surface charge density. Then we have seen how we can find out the induced surface charge density. We have seen how we can find out the induced charge. And then we have seen what happens when a dielectric is inserted inside the capacitor. The capacitance will become K times if it is completely filling up the space. We have seen two cases in which that is done, one with battery disconnected and one with the battery connected. Do we understand this?
Yes, sir.
The next class, we will see more cases of dielectric being inserted in the capacitor. Since we have covered a lot of things today, it might be confusing. And today you have the time. Please, humbly, I request, go back home and go through what we have done, because we'll be needing it in the next class. And if everything goes fine in the next class, we should be done with dielectrics. And once we are done with dielectrics, we would be done with capacitance also, because this is the last thing that is left. So I give you time. Please go through this and we'll meet in the next class. Take care. God bless you all, beta.
Thank you, sir.
Everyone has understood what we have done?
Yes, sir.
Akka?
Pakka, sir.
Okay then. Goodbye. Take care.
Bye, sir.